yesterday, before we kind of start getting into the next step, guys, the next phase of talking about these diagrams and talking about the atom and what's happening with it, yesterday we drew Lewis diagrams and Bohr diagrams. What's the difference between Lewis diagrams and Bohr diagrams? Are they the same? No, they're not. So what's different about them? Yeah, absolutely, guys. You couldn't hear Morgan. She said Bohr diagrams show all the electrons. Lewis only show the valence. And what's that term valence mean again? Outermost, okay? And those are the ones that are important to us. So as we continue throughout the year, when we come back and start talking about bonding and how molecules are formed, it's those valence electrons that are doing the work. Okay, they're the ones that we're most interested in. So today, the next phase of the game, guys, is the ground state versus excited state. And these were two vocab terms that you guys should know. Okay, so I've got two examples here. I've got neon in the ground state, and I've got neon in the excited state. All right. So if you look on your reference tables, okay, on your periodic table, neon's configuration is typically what? 2-8. Okay, 2-8. It's got 10 electrons, 2 in the first energy level, 8 in the second energy level. Excuse me. And that's exactly what we see over here on the left. We've got 2. Now, I know that these dots, guys, are not grouped like we did yesterday. Don't get hung up on them. Okay? Typically, you'll see them grouped. Sometimes you won't. They should still have the same amount there. Now, the analogy that I use here, guys, for the ground state versus the excited state is the ground state is like when you're in bed. You want to stay there. You don't want to exert any extra energy. But let's say kids. If you give a kid candy, what happens to them? They get excited, right? Why? They get hyper. They get that sugar high. So they start bouncing off the walls, going crazy. All right? Do they stay in that excited state for too long? No, because eventually what happens? They will crash back down. Okay? They will crash back down. So, the same thing is true here with electrons. Guys, electrons are lazy. They don't want to exert any extra energy, kind of like us. All right? If I gave you the opportunity to, or the option of running a marathon versus staying in bed, everybody's going to choose to do what? Yeah, okay. Stay in bed. Right? We're lazy. We don't want to do a lot of extra energy. Electrons are the same way. But sometimes they can get excited. So if you give them candy, like you give a kid a candy, they get excited, they get hyper. We don't give electrons candy because they're much smaller than candy, okay? But they get hit with some energy. It can be in the form of light. It can be in the form of heat. All right? So guys, how we show that is what's called a, so some type of energy comes in there. It hits the electron, and then the electron jumps up to a higher energy state. So that's what we see over here on the right is, now I showed this one, okay, it jumped up to a higher energy level, okay. It's when energy is being absorbed that we get them to jump up. So, a couple of notes to add in there. Ground state, lowest energy configuration. Okay, this is what's found on the periodic table. So all those configurations that you have written on your periodic table, guys, those are all ground state configurations. So for neon, its ground state is 2-8. Like I said, though, when some energy comes along, electrons get excited, and they become found in a higher energy configuration. Basically, guys, how you're going to determine this is count up the number of electrons you have in the configuration. Find out what element has that many electrons. If it's written any other way than what you see on the periodic table, you know it's in the excited state. So for lithium, it could be 1-2. It could be 1-1-1. Right? Those are the options. Typically, you're not going to see it jump more than one energy level at a time. Okay? So, like, if it's in the first energy level, it would go to the second. If it was in the second, it would go to the third. Now, it is possible for them to jump higher, depending on how much energy you give them. But you're not going to see it written that way. All right? On your regions, you will be asked, is this the ground state or the excited state? You've got to identify it. So again, like I said before, Count up how many total electrons are in the configuration. First one is 3. What element has 3 electrons? Lithium. So guys, you're going to go to your periodic table. Does lithium have this configuration? Yeah. Therefore, it's the ground state. Count up this next one that you're given. 2, 0, 1. That's 3 again. We know now that this is excited because lithium's normally 2-1. So if it's written any other way than what you see on your periodic table, you know it's in the excited state. All right? I want you guys to go through and try the rest to identify, is it ground or is it excited? So, now, the next thing, guys, you got to think about the why behind all this. What's really happening? So one thing is identifying, is it ground versus excited? Then you got to understand the why behind it. So think about this. Any runners out there? Anybody in track? Okay. All right. Cross country. I'm just thinking track specifically because in track you're running sprints right around the track. Does everybody start at the same place for like a long distance run? Yeah, right. Why? Right. The farther out you are, the longer the distance. If you were to start, guys, everybody at the same spot. So if you think about a track, all right, and everybody starts at the same spot, those on the outside have to work harder because they're covering more distance. So they would have to exert more energy. Right? That's why it's kind of a tapered start. Okay, like you said, like a waterfall type start, because they're running the same distance then. Right? Think about it here, guys. The greater the distance you get from the nucleus. If I were to draw a nucleus, okay, on this, which line would have to exert the most energy to kind of get, if we wanted a race to start at this point, if we wanted to start and stop at the same time, which one has to move faster to get back there at the same time? Yeah, the outside, right? This guy's got to work harder and take more energy to get back here if he's trying to beat this guy or be there at the same time. So all that's being said, that's my analogy, guys, saying the greater the distance, all right, from a nucleus, the greater the energy of the electron. So you've got to remember that, highlight it, star it. It should just make sense if you think about it. The greater the distance from the nucleus, the greater the energy of the electron. Okay? When the ground state electrons absorb energy, guys, they jump to a higher energy state called the excited state. That was the picture that we drew back here on this slide. I'll go back in a second. All right, that's this guy coming in. Right here, energy was absorbed. He jumped up and became the excited state. So maybe you want to draw like an arrow like this to show, oh, we went from the ground to the excited. Okay. Guys, it's a very unstable or temporary. Again, much like giving a kid candy, they're not going to stay in that hyper state for so long. Eventually, they're going to crash down. Electrons are the same way. If they don't have that exact amount of energy, they will come crashing back down to the ground state. So excited electrons rapidly fall back down or drop to a lower energy level. We know this is happening because we actually see it. Okay, we actually see it. When excited electrons fall from an excited state to a lower energy level, they release energy in the form of light. There's another key word you need to add to this. It's also called a photon. Okay, it's also called a photon. That light is what we actually see. In your lab next period, you're going to experiment with that. You guys have all seen fireworks before, right? Okay, that's obviously, hopefully something not novel to us. But this is exactly how fireworks work, guys. Electrons jump up to a higher energy level. They stay there for a brief second, and then they come back down to that lower one. And when they come back down, all that energy that they absorb, they then release, and we see the light. Okay, and that's what you guys are going to investigate next period in lab. We good with this slide? Can I go on? So the thing you got to remember, guys. Wrong piece. Ground to excited. You've got to know what's happening. If they're saying you're going from the ground state to the excited state, what's happening with energy? Going from ground to excited. Energy is what? It's what? It's increasing, guys. It's absorbing. It's being absorbed. Okay? When energy is being absorbed, you have this thing called a dark line spectrum that is produced. And that's this guy right here. Okay? It's being absorbed. So it's the first one that you see. Dark lines show the specific wavelengths of light that is being absorbed. All right? When the electrons become excited. We don't really care too much about the absorption spectrums in this class. What we care about, guys, is when we're going from the excited state down to the ground state. That's the unique piece. And you guys, if you took earth science, you've already seen this. Do you remember? Maybe you don't remember, but you looked at some. You guys did a lab last year where you looked at some tubes, some gas tubes, in this big black box thing, and you got that like spectroscope out. It was like the black triangle thing you had to look through. It probably didn't work that well. All right, but you could see the different spectra. No, you didn't do this last year? Some of you did. Some of you did not. I'm sure you probably all did. Oh, they didn't? He didn't do it with you guys? We'll do it out. We'll get it out and show you guys as a demo so you can see it for those of you who did. It's actually a really cool phenomenon that you can see. That's what we see here on the bottom, guys. When electrons go from the excited state to the ground state, what's happening with the energy? If it's being absorbed when it's going from ground to excited, what's happening when it does the opposite? Yeah, it's being emitted. All right, it's being released. Add that word in there, guys, just so you know. You could hear it both ways, released or emitted. I like that word, emitted. And this is where you get the bright line spectrum that is produced. So bright lines show specific wavelengths of light that is being emitted by the electrons. This is one way that the Mars rover actually identifies what elements are on Mars. Okay? They shoot some energy out to excite it. They capture the bright line spectra, and they can identify it because every single element, guys, has a unique bright line spectra. Okay? So they will only emit in certain wavelengths depending on what element it is. All right? Every single one is unique based on the amount of energy that it holds, and then it gives off eventually. Okay? So keep that in mind that every single one is unique, and I believe that's what we're going to add to our notes here in just a second. Can I go on? Am I going too fast? So this is called a Balmer series. All right? Electrons falling from an excited state down to the ground state. They give off visible light, which is the bright line spectra, or a visible light spectrum. Okay? It's only when they drop back down do we actually see the light. I'm going to harp on that, guys, all year long. It's excited down to the ground state. All right? Excited down to ground, that's when you actually see it. We don't see it when it absorbs energy and it jumps up. We only see it when it falls back down because it releases the energy, and energy, guys, relates to a specific wavelength, and then that wavelength we actually see as a different color with our light, or with our eyes. Different elements, guys, produce different colors. They are unique for each element. We use the spectral lines to identify different elements. So again, the example that I'm using here is the Mars rover. This is how we can identify what elements are on Mars. Okay, what it's made up of. You know, someday when your kids or your great-grandkids or your grandkids or great-grandkids or so on and so on are living on Mars, it's because of this. They figured out what it is. Do you think that's actually going to happen someday? No. I don't either.